So as we worked through our statics review, we calculated out the internal loads in that structure. And that's all well and good. But load doesn't tell us anything important. I know that seems like it's a weird statement to say that the load doesn't matter, but predicting failures, which is really what strength of materials is all about, is we want to predict when the material is going to fail, so we can design it so it doesn't fail, is not based on the load. It's based on a couple of different things. One's the material property, which we'll talk about later, but the other important thing is we need to know what the distribution of these internal forces are. So we're going to have to make a couple of assumptions about the materials that we're dealing with. And the first one is we're going to have to assume that our material, get a different color, defaults to red, so I don't like using that. But we're going to have to assume that it's continuous. So what does a continuous material mean? It means it consists of a continuum, or a uniform distribution of matter that has no voids. So we're going to have a blob of stuff that will have no voids, and it's all sitting there uniformly distributed. The other key word is we're going to have to assume that it's cohesive. And so all the portions are connected together with no breaks. So if we have something like sand, well, sand is not cohesive. You can squish it together, but it's not connected with no breaks because there are breaks in the material. So what we want to start doing is looking at this force intensity. And what we're going to do is we're going to look at a small differential element of force that we'll call dA. So we've got the small differential area, and we are going to calculate out the resultant force on those. Now, as I'm looking at this here, I've got three pictures labeled A, B, and C. And so basically what this is I've got this chunk of stuff. I'm applying 3 external forces to it, and a 3. And I want to start taking a look at what the stress distribution is. So this first one here, I slice off right at the top, and you can see I've got all these wonderful internal forces. They're all going in crazy directions. And what I want to do is I want to take a look at this dA. And so here's my representation of dA. And what I want to find is delta F. And so delta F is the resultant force of all of those internal forces. And so what I'm going to do, because I want to know all of them, we're going to apply a little bit of math, and I'm going to take the limit as delta A approaches 0 of the result of all those little forces. Now, I want to break these up into the different axes because I want to look at the resultant force in the z direction. I want to look at the resultant in the x direction. I want to look at the resultant in the y direction. So in this case, we're going to take the limit of all of these forces acting in the z direction, and then I'm going to divide it by delta A. So as I run this, as I take the limit of this as delta A gets to 0, what I am going to do is I'm going to define this to get a finite number. And that finite number we're going to call sigma sub z. So the first thing is, let's talk about that. We'll continue our classical Greek education here. What is that symbol? That is lowercase sigma. You guys are familiar with uppercase sigma, which is actually the summation sign, is uppercase sigma. This is the lowercase sigma, and we're going to define that as stress. In fact, we're going to define it as a particular type of stress, and we're going to say that we're going to define this as the normal stress. Why am I calling this the normal stress? Well, if we go back and look at our cut, there's our cut. We're looking at the z direction with respect to that cut. That is normal to that z plane. So that is our normal stress. And so this is a kind of a way to look at the intensity of a stress in an object. Now, just like with mechanics, sign's going to be important. And so the thing to remember is if the stress pulls, that is what we would call a positive stress, and that's what we'll refer to as tensile. Now, if it pushes, so if it's trying to squish it down, so that would be a push, squishing it down, that's a negative or a compressive stress. And these terms are actually really important because some materials' properties are different whether it is tensile or compressive. One of which being concrete, and that's actually why, and we'll talk about this later, why you use a steel reinforcement in concrete, but only in part of the concrete structure, or also glass. Glass has wildly different properties, whether it's a compressive force or a tensile force. So it is important to distinguish between the two of those. Now, we do have some other forces going on, so you're like, okay, Dr. Camp, we looked at everything in the z direction. But what happens when we look in the x and y? Because we are going to have components of force going that way. So those are acting tangentially to the surface. So they're not going to be a normal stress. They are going to be what we're going to call a shear stress. And we're actually going to talk about shear stresses later. Shear stresses act tangentially to the plane. And actually, we're going to do the same thing. So if I take the limit as delta A approaches 0, and I'm going to look at the sum of the forces in the x direction with context of the A, what we end up getting there is we are going to have a shear stress, and we're going to represent that with lowercase tau. It's kind of a C with a tail on it. It's lowercase tau. And with our shear stresses, we actually denote them as what plane it's on and then what direction it's operating in. So this would be the shear stress on the z-plane operating the x direction. And if we do the same thing, if we take the limit of this, of Fy, we would end up with a tau zy. And so we'll talk a lot more about shear in its own section. We're really going to be only going on with normal stresses currently. And let's see. I think that's where we're going to end this one. And what we'll do is we'll actually take a look at calculating normal stress in the next video.